The floor is yours.
Okay, thank you very much, Arina. Thank you for the introduction and giving me the chance to talk to you about my work. So this was the work that I've done in my stay in Linz, Ricam. The community there, people usually work on those kind of problems where we want to study realizations of certain graphs inside Euclidean spaces. Let me start with simple examples. And before I start, I really want to highlight this. Whenever there's something unclear, please go ahead and just interrupt me. I'll be very happy to answer all your questions. So if we take a certain graph, we have a bunch of vertices and edges, and we can associate to it something called the length function. So it's a function that takes from each edge, gives me a certain positive value. And to this function, I can define the lambda realization. The lambda is the name of this function, so it's a map from the set of vertices to C2. Okay, so in a way that if I take two vertices and if those are connected, then I want that they'll be they have corresponding coordinates in C2, such that the length, the distance, is actually the Euclidean length between those two points. One can think of it as an actual realization of a graph inside C2, where the edges are straight segments. And when I say graph, so of course it's a simple graph, it's not oriented, and it doesn't have loops, it's not a multi-graph, and so on and so forth. So let me start with a very simple example. If we take the triangle, here we see there are two realizations of the triangle. And my edge length function gives me, from this edge, gives me 2 square root of 2, and squared, of course, and here square root of 5, and then 3. So we can see that there are two realizations. Here we see them in R2. Actually, there are infinitely more realizations in C2, but what I'm interested in is that many of those realizations are similar following way. So geometrically, this means that if I'm looking at an R2, then those two triangles cannot be transformed from one to another by translations and rotations. Okay, so these are different in this way. And when I say planar rigid motions, I mean translations and rotations in C2. So it's just an affine map from C2 to C2, okay, where the matrix has a determinant +1. Okay. So we see the triangle. In this case, it has two realizations in R2. If I take a slightly more complicated graph, for example, K4 minus 1 edge, then it has 4 realizations in C2, up to those planar rigid motions, and all of them we see appear actually in R2. Okay, but when I talk about realizations, I don't only talk about ones in R2. For example, if we choose an edge length on the same triangle that do not satisfy the triangle inequalities, then one cannot realize it in R2, but believe me, one can realize it in C2 minus R2 up to planar rigid motions. Of course, if they don't, if they're generic. And I'm going to explain what does generic mean in that sense. So some graphs can have, even after I mod out those translations and rotation, they can have infinitely many realizations. For example, if I take K4 minus 2 edges, even after translation and rotation, even if I fix this triangle, there's an edge that remains, that describes a circle. So, so this is what I'm interested in, is to describe realizations of certain graphs inside the plane. Okay, let's take a certain generic edge length. So this is a function, right? As I said before. Instead of C, I can look at at R2 because now I can look at the Euclidean distance. I take the square of it, so it's actual polynomial, so that I am allowed to also take complex values. And I define the following number. So C of G is the number of lambda realizations of my graph up to those planar rigid motions. So this C of G would seem to be dependent on the edge length, but since I chose it in a generic way, it actually will not depend. And the reason why, so we will see it later, is that we can look at realizations as polynomial system of equations, where we fix the coefficients and we move some other coefficients. Now, if the choice of the coefficients is generic enough, so it's outside a certain discriminant, then we have a fixed number of complex solutions. And this is why we can say that actually one can define an invariant that depends solely on the graph, and that describes the number of the lambda realizations for any generic edge. Here's the example of the triangle. If I mod out the translations and rotations, I can actually look at those triangles which have one vertex at the origin. So this is 1, and another vertex at the x-axis. Okay. So if I'm looking at all those triangles, so this means that to actually compute the realization, then I'm looking at the sphere, at the circle centered at the origin at tier 1, intersected with the circle centered at 2. So this describes the first circle, this describes the second circle. And this is a polynomial system of equations. We see that it has 2 solutions. So they have these circles intersect in 2 places. And we always have 2 solutions as long as I choose those 3 edge lengths generically, right? So we just we take the difference of those 2 equations. We get a linear equation for one variable, and then I substitute. I have 2 possibilities for the ones. And if the triple lambdas of those edge lengths satisfy some discriminant equation, then I have a critical solution. And this gives rise to a definition. So a graph G is said minimally rigid if C of G is a non-zero finite number. So there are some, as we said, so this can be modeled by a polynomial system of equations. If I have too few polynomials, then I have infinitely many solutions generically. Then I can have infinitely many realizations for any edge length, generic edge length, because my polynomial system is underdetermined, so it describes a certain locus that is not finite. But if I have too many equations, so this means that if I have too many edges for the graph, then for any generic choice of coefficients, the system, I mean, it's not a square system, it's overdetermined, so I have no solution. So if I have a nice graph that has the right amount of equations modulo those transformations, then I can have finitely many non-zero solutions, so finitely many non-zero realizations. So in this case, we have the C of G equals to 4, and we have seen already 4 of those realizations. In this case, so if we take just K4, this means that we added an equation. Now, we added an edge. Now, this edge has to exactly be at the right length so that to fit the other equation. So now, if I move it a little bit, it's not going to work. So C of G is 0. And for this case, if I take K4 minus 2 edges, then there are infinitely many possible realizations. So this can have infinitely many realizations. So one can see is that this minimal rigidity depends only on the combinatorics of the actual this pair Z and so here's the problem. We're interested in, so this is one of the 2 problems that I'm going to present, is that we're interested in those graphs that give me finitely many realizations but non-zero. Yeah, these are called minimally rigid. Okay, so these are rigid because if I move them, they're not going to move, but minimally, because I remove one edge, then it stops being good. Okay. Okay. Anyway, if there are any questions, please do interrupt. So minimal rigid graphs are, I mean, the story starts from many applications. These appear in architecture, mechanics, material sciences, biology, robotics. The rigidity of actual material depends on the molecular structure, and to study this rigidity, it's interesting to understand how those molecules are binded together. And some of them are formed rigid subgraphs, some of them are not rigid, and this can study those graphs that model the molecules is important for molecular science. Also, studying realizations in general is important for biology, where we have a bunch of proteins, and the functionality of those proteins depends on the actual realizations of the shape of the protein, and this can be modeled by graphs themselves. There's many other applications, but in mathematics, it's an interesting problem in its own. So, given a graph, we want to know how many realizations does it have. So the first person that worked on this was Copenhagen-Jerusalem in the 20s, and by Gerard Lamand, and it has been rediscovered in the 70s. So what they did is that they give a formula that relates the number of edges to the number of vertices as a condition, as a necessary condition for the graph to be minimally rigid. And they also show that there's some inequalities for each subgraph that has to be set. Each subgraph shouldn't have too few or too much edges with respect to the vertices. And then there was attempts to actually compute the number of realizations, but we've seen that this is already a polynomial system of equations. One can apply several methods. One of those methods is called the Cayley-Menger variety, which is a certain variety that parameterizes all distances between points. And then if you intersect it by a certain a pre-described number of hyperplanes, so if you have a certain linear subspace of the right dimension, you intersect with it. This gives you the degree of this Cayley-Menger variety. This should correspond, gives an upper bound on the number of realizations. And so one can use some tools from algebraic geometry to provide upper bounds. And also, since this is a polynomial system of equations, one can look at the mixed volumes. There was a work by Stefan and Theobald where they, so we see here, like this number here is slightly better than this one, and it's too large. So they use some tricks in order to reduce this polynomial system into nicer polytopes. I mean, already you can see that there are polytopes on the top, but one can still enhance because the coefficients are not very generic, and then you can use Bernstein-Kushner and Khovansky upper bounds to bound the number of realizations. And there was lots of concrete work, right? So these are upper bounds. There are lots of people that computed this problem for the real realizations, because this is a separate problem, and for the complex ones where one actually gives a certain exact numbers. Yeah, there's some other results which I'm not going to go through details, but one thing to know is that only recently there was a first algorithm for computing the number of realizations without using algebraic geometry, like a purely combinatorial method, graphical method to compute it. And this was like an actual algorithm that works well up to 12 vertices, but higher than that it still works, but there's one has to have some nice graphs in order to get fast enough computations. Okay, so I described this problem, and let me describe to you another very closely related problem, and then explain to you how those two can help each other. So if we take a minimal rigid graph and we remove one edge, and then we mod out these rotations and translations. So this graph has infinitely many realizations, but since we removed only one edge, there's one-dimensional. The degrees of freedom for this graph is one, okay? Because we removed one edge, and this is called the calligraph. It's a marked graph where we remove one edge from a minimally rigid graph, and we mark an edge, 1, 2. We put it horizontally or whatever, we fix it, and then we mark the 0 point. So once this kind of fixing, it means that we mod out all our rotations and translations, and what's left is a curve. Actually, a calligraph describes us something called the coupler curve, and which would be written denoted by T lambda of C. Of course, now the coupler curve depends on the edge length. For each edge length, I have a certain unique curve, and this represents all the realizations of all the positions of the vertex 0 that can happen when I look at the realization. Okay, this gives me a curve. This is then for the complex case, it's an algebraic curve, because again we have a bunch of polynomial equations. We project them to obtain a curve. We'll see a figure later. For the real case, this is not necessarily an algebraic curve. It can be semi-algebraic. But okay, these are called the calligraphs. So why are these important? I mean, first of all, why they're interesting. So if I have a certain coupler curve, then let's say this is a coupler curve where in green I have fixed this one edge, and I'm looking at the curve that is given by the vertex in red. Now there are realizations that can be obtained one from another by just moving a little bit the graph, but some of them cannot be obtained one from another. So this here on the right, we see a family of realizations. One cannot be obtained from the other, and what we do to obtain, we just flip one triangle, and we can obtain a completely different curve. So, and from the algebraic geometry point of view, this means that we're looking at connected, irreducible components of algebraic curves.
So just to make sure, for every realization, you look on its own curve.
So each point in the curve is a representation of a realization itself, right? Because if I take a point, let's say here, right? So this means that my red vertex is somewhere that is here, but then all the other vertices of my graph have changed position, right? So this means that we have another realization. Okay, so for each red point, for each point in the curve corresponds to one realization. But yeah, you see, like if I want to go from one realization to another, then I can move continuously. Okay, and this whole locus is a curve. And on the right hand side is an example of one realization, right? Then and we see a curve here where for each point on the second curve here, I can be obtained by taking this realization on the right and then moving it. But then I'll loop back in. So, but here, so we have two families of realizations. One, each one is linked by just moving the graph. And algebraically, this means that we have actually two reducible components. Okay, does this answer your question?
Yeah.
So the first property is coupler curves can have irreducible components. The second property, that they can have multiplicity. So if I have let's say, let's look at this graph, for example. This we see it has a realization as a circle. But now if I look at another family, I have infinitely many realizations forming this circle, and this corresponds to all of those where the triangle has like it's below the x-axis. And also, if I look at the family where the triangle is above, then this gives me the same number of realizations. And we see here that then we can call this, we can associate to this as a multiplicity of this circle, right? It's the same locus of the red point, but it just has two multiplicity tool. And the formal definition is that of C is that we pick a generic point on the circle or on our coupler curve, and then we compute all the number of realizations that for which the red or the marked the zero vertex is at this point, and this would be the multiplicity. Okay, and it coincides with the algebraic multiplicity in the sense that if I look at the equations, I actually have a component that have that is multiplied by a certain number. So this is another problem is that, let's say I have a calligraph. So a question is to describe its geometrical properties, for example, number of components, singularities, genus, the multiplicity, and inflection points if we're looking in R2, and etc. There's numerous questions.
Sorry, can you say in which space do we consider this curve?
These are in C2, in C squared. Right.
So this number of reducible components and their multiplicity in C2 we consider.
Yes. Okay. So how do we find those curves? So we have a polynomial system of equations that modelizes where each equation corresponds to an edge length, right? So it's a quadratic equation. And since I removed one edge, now, and of course I modeled out like the transformations, so I have one less equations than variables, and you fix the edge length, right? So now you project it by forgetting all of those the variables that corresponds to all the other vertices, and you're obtained with two variables, and these are the coordinates of this red point here. Okay, and this by projecting it, so this is an elimination procedure. In your ideal, you will have a product of polynomials, like a product of polynomials to the power of things, and each irreducible factor is a component, and each power of such polynomial would be your multiples. Does this?
Yes, thank you.
Yes, please do interrupt me whenever something is not clear. Okay, so those coupler curves actually appear were interesting objects from the 1800s, even before, and this is a particular case of a linkage. A linkage is an assembly of system connected to manage force, and we have a bunch of systems, and they if we apply a force to them, they move in a certain, usually it's one-dimensional way. Pliers are linkages, and so here this picture is supposed to be the suspension system of some cars, which some models still have it, and this is actually a linkage where if I look at a point inside this red vertical line, then and there should be also a suspension system, a springs, so that when the car moves down or up, then the only way that the car would move is actually vertically or horizontally. But actually, if we remove some of the restrictions, this would give me a sextic, where at this location it has a vertical tangent. So with those small movements, the movement is almost linear. So, but this is a linkage in the same sense that the coupler curves are linkages. So Kempe was the first that proved a universal universality theorems and showed that actually, if I take any planar algebraic curve, then one can construct a linkage to that actually traces that trace. And this is not necessarily coming from calligraphs, but it can have different. And then after, these results motivated much work to kind of find a more optimal way to construct those linkages. And then these results were I'm not going to go through details, but these results were generalized, where one can actually show that any algebraic variety can be described in a similar way using a certain linkage, and etc. Is there any question?
Just a remark. I think there was a gap in Kempe's original proof, and this was
okay.
Just recently was corrected.
Okay. Was this one of those papers in blue in the first item?
In the Kapovic and Milson, and then there is a PhD thesis by Abbott where he followed Kempes but corrected the argument.
I see.
So the Kapovic-Milson uses a different technique.
I see. Okay. Oh, that's good. Good piece of history that I didn't know. Okay. Thank you. Yes, and lots of other results were generalized where we want where there's here it's more of a kind of like if we have a certain algebraic real algebraic set, then it's proven that it's any real algebraic set is homomorphic to something that's drawn by a lineage. But anyway, just to convince you that this is and lots of people worked on this problem. So let me summarize. Until now, we have minimally. So I introduced two problems: one about realizations of minimal rigid graphs, and another about describing the location of the coupler curves given from calligraphs, which are obtained by removing one edge from and our work with Niels Labbers and Georg Rasega is twofold. So we produce a method that computes the number of realizations of minimal rigid graphs and describes coupler curves, and we implement an algorithm that does. So how are those two problems related? So let's say I have a minimal rigid graph. Yeah, I'm going to ask you to believe me that this is actually a minimal rigid graph, and let's assume that this is it's a special kind that can be written as a union of two calligraphs in the following way. So if I have in blue a calligraph together with the green edge, and I intersect it with the other one, the orange one with the green edge, then I get only one edge and one vertex, such that the vertex does not belong to the edge. Okay, and if a minimal rigid graph has this kind of description, there's such a union that has this special intersection, then we call it a splitting pair, right? But the union of those two is called a splitting pair. So we can always, it's a nice graph for us if we can split it in this form. So why is it practical? Well, if each realization of a splitting pair is a union of two realizations of calligraphs, right? Because it's written as a union, right? So we can define actually a function that. So here's actually the fact. And at the same time, if I have a common realization if I have two realizations of calligraphs, then their union in this way will give me a realization of a minimal rigid. So this means that if I look at the two curves corresponding to the calligraph, then each intersection point is a common realization of their union of. It gives me one realization of a minimal rigid graph. Okay, and of course there's multiplicities and components that are involved. So this is the actual fact. So if I have this nice splitting where the set of common edges is 1, 2, and the set of vertices is 0, 1, 2, then for a general edge length, lambda prime on AB, such that the edge length of the 1, 2 is the same for both, then the multiplicity of the first calligraph times the multiplicity of the second one times the number of intersection points is equal to the number of realizations of the minimum. Okay. So these, I mean, this is one way where those two types of graphs are related. So here's the question: how to efficiently compute multiplicities of Kepler curves and their intersections. So if we have a method to find the number of intersection points, then we have a method to compute the realizations of those nice minimum graphs. And the question is how to kind of find an efficient way to do so. Okay, yes, so here I'm going to introduce some concepts from algebraic geometry. I'm not going to go very technical, but if you have questions, please let me.
Yeah, regarding the original problem. So given the splitting, I see that, okay, so you can do that, but how do you find such a splitting? You also need an efficient way to find it, right?
Yes, yeah, that's a good point. We implement an algorithm, and the most part thing that takes from your algorithm is finding of this splitting. And so what we do is we just go through all pairs of edges and vertices, right? And for each one, you remove the adjacent edges. If you get two connected components, then you win, right? So you see, this is a splitting. You remove this edge and you remove this vertex, and now you remove all the adjacent things to each of them. Right, so from the blue one, I get one connected component, and for the orange one, I get another. If I don't, then it's not a split. Okay, this is, and so like, okay, so it's complexity. I don't know. I mean, we're looking at all pairs, so quadratic and something. Yeah, this is the idea. Okay, so why? Okay, how do we kind of give an efficient description of Kepler curves in order to compute their intersections? I mean, one can look at polynomial system of equations, but then we're still at square one, because we want to avoid elimination theory is very expensive. So for this, I define a certain lattice for which goes as follows. So there's a birational operation called blowing up. So what I do in this case, I look at the projective plane P2, and I can define a series of blow-ups in the following way. So it's a very particular sequence of blow-ups. I always take two complex conjugates, conjugate points of P2, and then I blow P2 at those points. So blowing up is just a birational transformation for which it's bijective everywhere except over the points that I chose to blow up. Then the pre-image is a line. Okay, so one can think of Y1 as a surface above P1, P2, and then Y2 as a surface above Y1. So if I'm choosing those two complex conjugated, starting from P2, choosing those two complex conjugated points, I look at the blow up. Now I can lift the complex conjugation of P2 into my Y1. So Y1 has a real structure iota 1. And now I can define some two complex conjugated points there, then blow up, lift again, etc. So a finite number of times. Then I obtain eventually a real surface that is birational to P2. Okay, so this is what I'm interested in, and so it's a known fact from intersection theory is that using this description of blowups, I can define a lattice. So it's just a lattice. It's called the Néron-Severi lattice, where it's spanned by the elements sigma 0 and sigma p, where p are the points corresponding to my blowup, and the base elements are so sigma 0 is kind of represents a generic line in P2, and sigma p represent each sigma p represent a point in the blowup, and also we have those relations. These encode the algebraic geometry of curves in P2. So sigma 0 squared equals to 1. It's because two generic lines always intersect in one point. 1 point sigma squared p equals to -1, because if I blow up the point, I get a line. This is an exceptional divisor. It has self-intersection -1, and no two exceptional divisors can intersect, including 0. So I have sigma p times sigma q. It's just a certain way to encode an algebraic procedure. Now, my lattice is special because I used two complex conjugated points as low, right? So there's if I pick any two complex conjugated points in any of those surfaces, then the complex the real structure transforms one to the other, and this can be lifted to my Néron-Severi lattice. So I obtain a group lattice, right? So and I can lift this real structure from ny to ny to a unimodular involution. Since this involution on the generic line gives me a generic line, I have I star of sigma 0, sigma 0, and I star of sigma p is sigma of the transformation of p. And from this, we have this induces a bunch of operations on my group. The main point here is that I can reduce almost half the dimension of my lattice by taking into account the structure of real points. So why is this whole procedure is useful for me? Well, it comes from the following fact, that for any real algebraic curve in P2 downstairs, I can look at its free image and under this blow-up map in Y. And since I have defined this lattice, so I can associate to it a class. So each algebraic curve has a certain class. It's a vector in this lattice, and it's given as the divisor class of the strict transform C along the blow-up map of Y to P2. So it just says that each curve can be viewed as a vector inside this lattice, where as a linear combination of epsilon 0, epsilon 1, epsilon r, where the coefficients corresponds to the multiplicity of the intersection of this curve with those exceptional divisors. So, okay, how is this description is useful for us? So if we have a calligraph VE, as we recall, this corresponds to one. Each edge corresponds to an equation, which is given by the distance function. And so I can define an ideal, so a bunch of equations like this. And then so this lives in the space of all coordinates and edge length. Now I can project all the xi's, xj's except the x0 to obtain a certain hypersurface inside the space whose coordinates are x0, y0, and the edge length. So this means that if I fix the edge length, I obtain a certain curve. So actually, this hypersurface defined is a real hypersurface because the equations have real coefficients. And this is a family of calligraphs where each coupler curve can be obtained in this operation. So I take a point inside the space of edge lengths. This corresponds to one edge length. I can look at the free image. It's a curve inside this hypersurface, and then I project it to Z2, and this is how I can obtain my curve. So what happens here is that the pre-image, there's a linear system that describes all my curves, and it is expected for each calligraph to have a family of those curves that is given by this linear system where I just move the edge. And so this is the fact is that if I have a set of base points of my polynomial PG, and I look at the Néron-Severi lattice that corresponds to this blow up, where I choose my points to blow up as the base points of this series. So base points is just if I have a family of curves and all of them pass to the same point, then this is a base point. Okay. From this description, I can define a set of base points. I can look at the set of base points. This defines me those points where I blow up my P2. So I have the following two assertions. So first of all, if I take any two generic members inside this linear system, then they have the same class. Okay, so this means that they define the same vector in the Néron-Severi lattice, the real Néron-Severi lattice, whose vectors are given by the base points of the calligraph. And the second factor, if I have any other family of any other calligraphs that have whose base points are included in C, then the product inside of the Néron-Severi lattice is actually equals something inside this algebra of the lattices, and it's equal the product of the multiplicities times the number of intersection of those. So this means that I can, given this for each calligraph, if I have this nice description of the Néron-Severi lattices as vectors of those two curves, then I can easily compute their number of intersection points, and it's just a bilinear form. Okay. All right. So the takeaway here is that one can represent calligraphs as families of curves, and and each family corresponds to a vector, and the number of intersection points of those two families of any two curves is equal to the product of two vectors in this way. So the main point here is to find the set of base points for each calligraph. Are there any questions up to now? Okay. So if we find the base points, then we can define each curve as an element inside my lattice. So let's take some examples for those base points. Let's take, for example, this calligraph. So we have fixed an edge, and we have our zero, the marked point that is linked to the origin. So this defines a circle. Okay. Its equation after I projectivize looks something like this, where L is the length of this edge. Okay, usually inside C2, we put Z0 to be equal to 1, so we just have a circle. And so here, this is a family of circles. So it's a family, so the calligraph, the family of coupler curves is a bunch of circles inside P2. So it has two types of base points. The first ones are cyclic, so gamma and gamma bar. And of course, I mean, they don't have base points inside the affine plane, because, I mean, for any point inside the affine plane, I can always find a circle centered at the origin that doesn't pass through it. But if I look at the line at infinity, then all of those circles pass through the same 2 points. And to compute them, I just put z0 equals to 0. So I get the equation x0 squared plus y0 squared. Now, if I look at the affine chart of infinity, I get y0 squared equal to 1. And this is why I have a base point at actually 2 pair of base points at infinity. Okay, so this tells me that all the family of circles at the origin pass through 2 complex conjugate points at infinity. And this information will be used as a data to construct my Néron-Severi. Okay, what other points does it pass through? Well, if I look at the blow-up of P2 at those 2 complex conjugated points, then one can make some computations. I'm going to skip it here. And actually, we blow up, so this means we change the variables, we restrict to our exceptional divisors, and we see that, okay, there's 2 other points that for which the 2 other points that that correspond to yes. Is there a question? Okay. It's okay. Right, and so these are called the infinitely near base points. And these are called the one-centric points. So now I have L, the class of this calligraph, is actually the degree, so a coefficient times epsilon 0, which gives me the data of the degree of the curve, and in this case is of degree 2. So this is why we have 2 times epsilon 0, and it passes through the cyclic points with multiplicity 1. So I have 1 times epsilon gamma, and passes through the infinitely near base points by multiplicity 1. So I also have 1 epsilon. Okay, so this is kind of the representation of the calligraph of this calligraph as a vector in the Néron. I can play a similar game by finding. But by looking at this calligraph, one can also check that this has 2 cyclic points of multiplicity 1 and 2 two-centric points, each of multiplicity 1, and it has degree 2, so its class looks like this. And there's a third set of base points. So let's say I take this as a calligraph. So it is a union actually of 2 circles, because if I take this triangle, it gives me a circle, and then I flip the triangle down, then it gives me another family of realizations. So now I have 2 times the same circle. So this means that I have degree 4, and if I compute, I actually have 2 times epsilon gamma, because it intersects only the cyclic points as base. Okay. So the theorem that we've proven with Tanziger and Lubis is that a base point of any coupler curve can only be cyclic, one-centric, or two-centric. Can only be the ones that we just computed only for those special cases. In general, what we'd expect if I take any complicated or not complicated calligraph, then it can have different sets of base points. But what we've shown is that those ones that come from those 3 simple calligraphs, these are enough. These describe all the other calligraphs. Okay, and furthermore, so we actually had, there's some geometrical result on the intersection of the calligraphs with the line of infinity that says that, well, actually the degree of this calligraph is always twice the multiplicity of the cyclic points plus some multiplicity of the one-centric and the two-centric ones. So this means that to describe any calligraph, we need just 3 integers, one corresponding to the degree and one of the multiplicity of the one-centric point and one for the two-centric point. Okay, are there any questions about this statement? So how is this useful for us? So yeah, but before going to this, let me give you an example. So let's say I have this as a calligraph, and this is described by a system of polynomial equations. I mean, this is not too accurate, but it looks somewhat like this. So we see, for example, this first equations correspond to this one, second equation corresponds to this, and so on and so forth. The green one is actually fixed to be 2, so I don't put the equation for it. And now this, once I fix the edge length, I assume that they're generic. This gives me a certain curve in the space of variables x0, y0, x3, y3, x4, y4, right? Because those are moving. And now to obtain my curve, I just project in C2. I just forget those variables, C4, x4, and x3, y4, and y3. This corresponds to an algebraic operation. I obtain this polynomial. So actually, these are two. I mean, the exact coefficients of this polynomial are not important, but what we get is actually two polynomials. One with where we have somewhere pluses, and another is where some pluses are replaced by minuses. Okay, and it has degree 6 times 2, so it has degree 12 because we're looking at two connected components. So the coupler curve actually has degree 12, and just by the computations, one can check that it has cyclic, and 1 and 2 cyclic points are the only base points. So this confirms the theorem from before. And their multiplicities are 6 and 2 and 2 respectively. All this computation can be done actually by just solving the univariate equations. And so this means that the class here is 12 times E0 because the multiplicity, the degree is 12, and then plus 6 times epsilon gamma plus 2 times epsilon 1 plus 2 times epsilon. So how is this theorem is useful? Well, it says that if I look at the pair of at the product of n3 times n3 to z, and I can define a certain product, this product that gives me so a point in n3, 2 points in n3, and it gives me this bilinear form. Then there exists a well-defined function that goes from the set of all calligraphs to this number, to this lattice, and satisfying the following. So I take the calligraph, and this gives me a class which is a triple, such that the class of this calligraph is 110, the class of this one is 101, and the class of this one is 200. And there is some properties on the curves, which I'm not going to go through details, but also that if a minimal rigid graph has a nice splitting AB, like we've seen before, then the number of realization of G is this this class product of A and the corresponding B, and this product looks like this. Okay, this is the corollary of our theorem. So how can we use this this result in applications? So so if G, let's say I have a splitting AB, then we have C of G equals this product, where A is equal to has a class A0, A1, A2, and B has the class B0, B1, B2. Okay, and in order to compute the number of realizations, I just multiply this by this. Okay, and this actually gives me eventually my the number of realizations. So if I have the class here and I have the class here, I can obtain the number of. But the question is, in this example, let's say, how do I get the class of A and how do I get the class of B? Okay, so let's start by computing the class of this calligraph, the blue one. So first, I connect it to three other smaller calligraphs. So the blue. So here's my blue calligraph. I connect it to the yellow one, the L shape, and then the inverted L shape, and then I also connect it to this guy. It turns out that each of those unions is a minimal rigid graph, right? And this minimal rigid graph in each of those cases has their own realization. So this is the description. So the number of realization of this whole thing is A times the class of this guy. The number of realization of this whole graph is A times the class of this graph, and similarly here. Okay, and this is because each of those three form a splitting pair, and from the theorem that we've shown that the two splitting pairs, the number of realizations give me the classes. Okay, so it turns out that since A1, A2, A3 are not such a big graph, we already computed their number of realizations. So here it's 8, and this one is also 8, and this one is 24. So now from this equations, my unknowns are the class of A, right? So A0, A1, A2. So I have this equation that comes from this equality and this one and this one. So here I have a linear system of equations. So now I can solve it for A and obtain the values. Similarly for the other graph from before, right? So let me remind you, I had two calligraphs, and I just gave you relations between the blue one, which are those, and I can play the same trick for the other calligraphs. I connect it to three other calligraphs, and this is enough. And I obtain the number of three linear equations. Solving them, given that I know the realizations of each of those graphs, then I obtain the classes of A. Okay. Now I have those classes. I can multiply them to get the number of realization of G, which happens in this case to be 100. Okay, is the algorithm clear? Okay. Yeah, I mean, you can interrupt me again. So the idea is to do this iteratively, right? I start always with the minimal rigid graph, big one, and then I want to compute the number of realization. If I'm lucky, if it's nice enough, I can find a splitting pair. So for this, I want to compute for each calligraph, I want to compute the number of the classes. Okay, find the number of realization. How do I compute the classes? I do this gluing thing. I glue it by three different smaller calligraphs to obtain now 6. Now I have minimal rigid graphs again. Then I want to compute their realizations, and I split again, and then I glue and split until I reach a bunch of smaller minimal rigid graphs. And for this, because they're small, let's say it has at most 6 or 8 vertices, depending on what's the preference, then we can use previously known algorithms to compute the number of realizations of minimal rigid graphs of those minimal rigid graphs. And then afterwards, I can deduce the classes. From the classes, I can go back, deduce the minimal rigid graphs, etc., until I reach the number of realization of my origin. And this is basically how the algorithm works. Okay. Yes. So this graph here, this histogram, shows that a little bit more than half of the graphs that we've sampled are splittable. Right, so we cannot do this trick if the graphs are not split. So the experiments show that it's like, okay, more than half of them satisfy this property, and this graph tells me that, okay, for whenever they're splittable, whenever everything works, there's a significant increase in computation time. Yeah, the complexity analysis is yeah, it would be a messy thing to do. So we just made some experimental data to check this. And yeah, that's it. That's all I wanted to say. Thank you very much for your attention.
Okay, let's thank the speaker for amazing talk. So now, are there any questions?
So in the non-splittable case, is there an algorithm to compute the number of realizations?
Well, there is the previous algorithm that I mentioned before in one of my slides that works for all of the graph. But if you have very high number of vertices, you don't know when it stops, right? And I mean, the way we programmed it is that if it finds a splitting, if it doesn't find a splitting and the number of vertices is high enough, it gives you the question like, do you want to use the previous algorithm or not? Are you prepared to wait for weeks or not? That's kind of the thing. But there is an implementation and it's and it works. But yeah, you know.
I mean, you also need to be hereditarily splittable, right? Because after you split,
Yes.
you need the.
At each step, it has to be splittable, of course.
Yeah. So as the size of the graph grows, maybe the hereditably splittable becomes few, or is it still, you think, half?
There's so many questions about the structure of what, and this is one that we definitely are interested in to understand, like what happens. Like, okay, if you take big number of vertices, it's almost as it's very related to your question, like is it still 50% or less? And we don't have a consensus yet. We don't know. With too many, like if you're looking at already 13 vertices, there's just too many of those graphs, so we don't even have a statistical.
Okay, thanks.
I have a question. So, like, if we're talking about, say, singularities of the scapular curves, is there like any kind of intuition behind like what it means geometrically, and like why would it be interesting to study them and so on?
So the singularities, the way we look at them is we just take the classical definition of algebraic geometry, right? So the actual quotient, the dimension of the quotient ideal, when you take partial derivations, and this is a very practical way to like practical approach, because our description already uses like intersection theory and algebraic geometry. So we already have like an idea about the delta invariant that is known from classically, and this gives you an upper bound on the number of singularities in this sense, cusps or no. So we have a fairly good description, and it can still be improved, you see, because there's an upper bound, and then one can get. We believe that we conjecture that this upper bound on the number of singularities is actually an equality. But I mean, this is some future work that can be improved. And in terms of like what is useful for application, I mean, if we're looking at the real part of our calligraph, so first of all, if I have this the coupler curve and just taking the real trace, it doesn't necessarily mean that we have this trajectory, right? So some curves can have unbound. Maybe the trajectory is actually usually some algebraic subset. But if I have a certain cusp, then we can say something. So this then like we know that the trajectory, okay, it's an actual description on the movement. It goes in one direction, then goes back. Or and this in terms of applications, I mean, we haven't talked to lots of people that work in those fields, but I would imagine that those kind of descriptions would be useful if you're trying to model a robot and you want to know when does it go back or when does it cross the same part. Yeah, I mean, singularities give some information about the trajectories, but how much useful to the application? Inflection points are also something that would be useful.
I wish to ask about this special product. It looks like multiplication, like convolution with Minkowski metric of two vectors.
Oh, okay.
And also I want to ask about how many consider minimal rigid graph and how many splitting pairs can it have?
That's one other question that we were wondering. Does one splitting pair guarantees another one different? We have no idea how much. But that's a really good question. It's like there's so many things about the structure of this splitting thing, but the algorithm, the way it works, is just naively. I mean, of course, there's some splitting pairs that can be better than others if you want to work with the algorithm, right? So from what we've learned, the best way is like to have something where the number of vertices on one is roughly equal to the other. Right? But the algorithm just continues once it finds a splitting pair, because finding all of them, I mean, yeah, you would reach the worst complexity. But that's a good question on how to characterize those calligraphs, those minimal rigid graphs that have more than one splitting pair. But the problem is that we don't even have characterization for those that have one. Yeah, the problem is in its infancy and so forth.
Okay, are there any other questions?
I wish to ask a simple question about dimension of Néron-Severi lattice.
This is equal to 3 in this case.
And in general?
In general, it's equal to the number of blow-up points plus 1, and the plus 1 corresponds to the line, right? So you see, each vector corresponds to it. I mean, in the lattice, if you take a vector that you want to model your curve, so it's a linear combination of the kind of basis vector, right? And each basis vectors is symbolizes one blow-up, one point where you blow up, and the coefficient in front of it is the multiplicity of this curve intersecting this point. So the multiplicity of a curve and a point. So what you do, you let's say you want to compute the multiplicity at the origin, then you look at the degree of the smallest degree monomial, right? You look at the degree of the smallest. You look at the monomial with the smallest degree, and this is kind of the multiplicity of the intersection of the line at the origin. And at any other point, you just translate it and then use the same definition. These are the coefficients. The dimension equal to the number of points per wall.
Okay, if there are no other questions, I will stop the recording.
Maybe one more question. Sorry, what if we take the edge, take any minimally rigid graph and take its edge number k and let its length to be t to the power k, where t is a parameter, and then we let t tend to, say, infinity. Could you somehow combinatorially describe the limit realizations?
You're talking about zero patchworking, right?
Yes, it's something like this, something like this. Does it work here in some sense, or
That's a good idea to actually find the number of real realizations, or at least find the lower one for them, because it should work. Yeah, I mean the zero patchworking is already defined for multiple.
no, I mean not necessarily real, just to count it like in tropical correspondence.
Well, yes, it has been done, and this actually the work of, okay, let me give you the so here is the last item. This algorithm was based on tropical intersection. What they do is they look at the tropical. Okay, so you have your polynomial system equations, and then they modified them a little bit so to make them slightly simple, and then they use tropical intersections. And from what I understood is that they like your subdivision, your weights of your weights are not one. Like they had to use kind of not coherent, not unimodular solutions, and this is the basis of why this. So the answer to your question is yes, and like the details.
Thank you.
Okay.
Any more questions? I guess I'll stop